Boas a todos. This here is a detailed guide on how to use the Planetary Gearbox OpenSCAD script. When you first open the script on OpenSCAD, it will show you a blank screen. So come to the Preview tab and select Compact View. The compact view shows you a model Nema 17 attached to a 5:1 planetary gearbox. If you wanted to see an expanded view, select option number 2, and here it is. All the components that make up your gearbox, with the exclusion of the attachment. Since you're just adjusting the settings, I suggest that you go to basic parameters and reduce the resolution of the model from 100 to 50. You can even reduce it to less in case it's kind of slow. Next, adjust the tolerance. This is half your 3D printer's tolerance for the material you're using. It's optimized for ABS, so try it out. Next tab is Geo Configuration. Basically, these first 3 settings help you set up your gear ratio, so number of teeth on the sun gear, the planet gear, and the ring gear. If you're not familiar with planet gear, you can go to the website I provided you guys, and it simulates a planetary gear. So make sure that it's solved for planets and carrier. Reduce the number of the planets to 3. By default, the gearbox has 3. Then come down here and look at the ring speed. It should be -1, just increase it to 0, so the ring gear stays put. Next, let's say you wanted to simulate a 4:1 gear ratio, right? So the sun gear should spin 4 times, and the carrier speed should speed up only once. At the moment it is 1.333, right? So let's adjust this. Let's reduce the number of ring teeth to say something around 40. Let's mess around with the number of sun teeth. Okay, I'm getting close. And there it is. 12 teeth on the sun gear, 12 teeth on the planet gears, and 36 on the ring teeth gives you a gear ratio of 4:1. The best gear ratios are in between, for planetary gearbox, are in between 4:1 and 6:1. The reason for that is once you start approaching, say 2:1, or on the opposites 10:1, the sun gear or the planet gears just increase and decrease in size too much. Say, let me just try to show you 10:1, right? For me to achieve a 10:1, here it is. See the size of the sun gear? It has only 4 teeth and it's minuscule. If I were to try a 2:1 gear, the opposite would happen. Next is the ring gear number of stages. Basically, if I were to need a 25:1 G ratio. I will just increase the number of stages to 2. See here, 2 planetary gears stacked, and it can go up all the way to 4 stages. In this specific case, this would be 625:1 G ratio. Next comes the backlash, or the gear backlash. This is basically a small gap in between the gear teeth that helps the gears mesh correctly without binding up. A good value to start at is 0.2 millimeters. You can decrease it a bit if you want, though this is an optimal value. Let me just decrease this to 1 so it renders faster. Another important value is the gear millimeter per tooth. This adjusts the size of the gear teeth here. You can increase it in size, say 4 millimeters, and in so doing it adjusts the whole model and even introduces a few bugs. So I'll show you how to fix that. But this here is a very important value. Another value is the gear height. It shouldn't be less than 5 because it will start to clip in a few models, but 6 is a good value. You can also increase it to say 8 if you're working with a more powerful motor, for example. Next setting is the Planet gear shaft radius. This makes, let me see if I can zoom in. The Planet gears rotate on a carrier here in red. And both 3 Planet gears rotate on a bushing. The bushing size is adjusted by the Planet gear shaft radius, as well as these output shafts that connect to the next stage. So if you were to be working with a smaller motor, you might want it to make these smaller, and if it were a bigger motor, just increase it in size so that, for example, these shafts can transmit the torque properly without snapping. Let me show you a few examples of what I'm talking about. See, increase in size. Just be aware that these model cylinders don't start clipping on the Planet gears. It's quite easy to see what are the issues. The output shaft adjustment is just a small ratio that helps you make this shaft bigger or wider or smaller if that's your need. For example, let's decrease it in size. See? I believe it's 1.5, the default. The next step, it's nuts and bolts. This is pretty much self-explanatory. Screw size gives you the size of the screws as well as the nuts. By default, I'm using M3 screws and nuts, and the screw length, it's the size of the threaded part of the screw that goes in here. Another important tab is the Nema motor. This script is designed to produce gearboxes for a range of stepper motors, and it supports from a Nema 11 all the way to Nema 34. by default it's optimized for Nema 17, so you need to do a bit of tweaking for some of these values. Later on I'll show you a few examples. Nema stepper shaft height and Nema stepper shaft radius refer to the motor's shaft properties or parameters. The Nema stepper height, it's the height of the stepper's motor. This stepper here isn't model accurately because this height here, the Nema stepper height, gives you basically the height that goes all the way from the bottom of the Planetary gearbox to the bottom of the Nema plate. That is this model here. You'll see what I mean. Next comes the Nema motor D-cut shaft. Most stepper motors have, let me just show you. Most stepper motors have a shaft like this. It's cylindrical to a certain height, then it's sanded flat on one of the faces, making up a D-shape cut, right? Okay, let me just see if I can show you two guys. Okay. The shaft goes here. So inside this, it's called the Nema gear or the sun gear. I can't see it properly, so maybe. Okay, let's model just the Nema gear. Oh, here it is. As you can see, there's a small height adjustment for the bottom of the shaft that's cylindrical. Then there's a D-cut shape there, right? For you to produce this D-cut, by definition, it's modeled as a cube that's operating on a boolean between this sun gear and the shafts inside, right? So let me just show you. Let's move the cube to the center. So shaft x offset is 0. See, it's centered. I can make this a bit more obvious. Let me just decrease the width of this cube. Say 2. Okay, it's off-centered. Let me adjust the y offset to half the width of the D-cut shaft. So 1 millimeter. There it is. See? I'm rendering a small cube. The cube's parameters length will correspond to its size on the x-axis, the width on its y-axis, and its height, it's basically the height of the cube, right? So the x offset just moves it away from the origin by a certain amount, in this case 2 millimeters, and the y offset is just a way for you to center the cube, so it's half the width's size. So change to 5, and this should be 2.5. The last is the D-cut shaft. It's the offset that lets you adjust the cube's height. So it's 1.5 millimeters from the bottom. I can increase it to say 3. See? This is how you model the D-cut. It's different from stepper motors to stepper motors, so get out your calipers. I believe that's the name. Next tab, ball bearings. As you can see, some of these components have integrated ball bearings. If you're not familiar with the design, I've also published a small parametric ball bearing code on Thingiverse, where it explains in detail how you can assemble these, as well as fine-tune its operation. But basically, you go to any big sports goods shop and look for steel ball bearings. You can find them as ammunition for air guns. They're about 4.5 millimeters in diameter, more or less, and you can buy a flask of, say, 1,000 for €5. It's pretty cheap. Then you can adjust the ball radius so it's a tight fit, but it doesn't bind up. Here, though, be aware that this value here is the ball radius, and you have to add up a certain tolerance. The tolerance you inputted up here isn't reflected on the ball radius, so it's manually adjusted. In this case, my balls, I found that the best radius for my balls were 2.15 millimeters. Then I added 0.50 millimeter tolerance, and the math's wrong. The balls will probably 2.2 millimeters in radius, so it's 2.35 millimeters. You need to fix this though. The last I've shown you is how to render the individual parts here. Just select them and hit change the basic parameter resolution up to 100 and hit F6 to render it. If you want to speed up the final rendering process, you can open various instances of OpenSCAD and just render manually each new part. If you wanted a more hands-off process, just send me a message and I'll try to get you a small script that will generate all the pieces of your gearbox automatically. Okay, this here is the basic settings, all the basic settings, and I wanted to show you also a few examples of how you would to generate a parametric gearbox for, say, Nema 14, right? So Nema 14, let's display a compact view, come to the Nema Motors tab, select Nema 14. Okay, as you can see, there are a few bugs here, a few errors. Next setting you need to adjust after these here: Nema stepper shaft, height, Nema D cut, everything else. Come to the gear configuration and adjust the gear millimeter per tooth. Since this is a smaller motor, let's just decrease this value from 3 millimeters to, say, 2.4. Okay, that seems nicer. Let's just open it up and see if there's any issues with some of the parts. There's no gap in the Nema gears. The holes for the screws that attach the Nema motor are well defined. The bushings and the outputs on the carrier are a bit too wide. Let me just zoom in so I can show you. As you can see, it's slightly overlapping with the Planetary. So come to the Planetary gear shaft radius, and let's reduce it to say 1.5. Okay, that's better. And if you want, by default this is the 5:1 gear ratio, but let's add another stage and see if any other bug crop shows up. Nope, everything seems more or less fine. Now let's suppose that you wanted to model something for a Nema 34. Now that's a big motor, right? So Nema 44. And as you can see, there doesn't seem to be too many issues. Just ignore the Nema motor on the underside here. It doesn't display accurately. So if you want, you can just adjust this to a bigger value and see what happens. Whatever. But be aware that all the stepper motors have different heights. There isn't any. This doesn't set it up properly. Okay, the output shaft is a little tiny. We'll have to adjust that. Let's open it up, and there's a big issue here. The Nema plate is missing a lip, and it's too wide, right? It's supposed to have a small brim here. So let's go to the gear configuration and change the gear millimeter per tooth for a bigger value, say around 6.5 millimeters. Okay, that seems to have solved the issue. The gears are a bit too small. Let's just increase them in height. Say, I don't know, 9 millimeters. Okay. Maybe a bit more. Say 11. Now that seems decent. As you can see, you can see it now. Now you can see it very well. Let me just adjust this. But the bushings and the carrier outputs are a bit too small, right? They're too fragile. Just adjust a few of these values. Okay. See? So Planetary shaft radius, let's increase this to say, I don't know, 3 millimeters. It can go a bit more than that, 4. Okay, 4 millimeters seems fine. Okay, let me just put 12 millimeters on the gear height. And everything seems to be working out okay. Let me just show you a final piece. Most errors that crop out will be here on a Nema motor plate. By default, the screw holes should be well defined, and there should be a small brim here. So let me show you what I'm talking about. So 3 millimeters. See, the brim disappeared. Now while working with Nema, say 14, right? There's a brim, and it's interfering with the screw holes, right? So the gear millimeter per tooth should be lesser than this. Okay, these are pretty much all the issues that you probably find yourself running into. If for some reason you need to edit the code, say you wanted to model, oh crap, let me just reset the settings here. Say you wanted to make a triangular shape here on the output shaft, right? Whatever. Then you'll go to the code. Let me just show you how the code is set up. Okay, I'm just using a test editor for editing this code. It's Emacs if you're not familiar with it. There are a few tips here. You can read them if you like. There are a couple of bugs that you might encounter. On the basic configuration, these are all the settings that are in the OpenSCAD customizer. There are a couple of hidden settings here. On the advanced configuration, sorry, I've lost myself. Okay, here it is, advanced configuration. The gear twist, this is something that's not fully implemented. It just enables you to generate beveled gears, but it's weird. If you wanted to work with these, this is where you would adjust. It's an angle. One important variable that you might want to mess around with is the warp factor adjustment. As I said, this is adjusted for ABS. So if it were binding up, you would probably need to increase this value, say 0.05. And if you were to print this Planetary gearbox using, say, PLA, then I suggested you would put 0 on this value. Some of these variables have a small warning. Don't mess with it. Just don't change these values unless you know what you're doing. The planet gear quantity, by default there are 3 planet gears. If you were to generate a Nema 44, then you might want to increase the planet gear quantity to 4. I don't know, it's up to you. The rest of this is, it's many details. This part of the code is for preview and generation of individual modules, and the code for that models each of the pieces starts the procedural generation modules. Model SunGear generally generates the SunGear. So be aware that there is no SunGear model. This is used in the Nema gear. These model the planet gears, the Nema motor plates, and I wanted to show you how you can make a triangular shaft on the outputs. So let's go to the output shaft module. Here it is. As you can see, all the code is more or less commented. Create main body. Okay, there's a union of various pieces. This here creates the shaft main body. And let's see if this small piece of code is what I'm talking about. It's not, right? So it's not this. Let's highlight the next piece of code. Okay, that's what I'm talking about. And as you can see, this is a boolean of difference of create main attachment body, and it's drilling a small screw hole, right? So it's applying a 40-degree rotation, and it's translating for a set amount. This is parametric by nature, so the height is the gear height, and here is the cube that's modeling the shaft. So you'll just need to delete this piece of code, generate your triangle, and just extrude it on the Z height, for example, according to your parameters. And this is pretty much it. If you have any issues, or if any sort of weird bugs crop up, just send me a message. I really don't mind. And thanks for watching.